Okay. I'm reminding you the file that you've seen last time. It's the problem, the blending problem that you have seen last time was quite simple, demonstrated by this diagram here. And I show you the diagram because the next problem is going to present it as a diagram also, and immediately you will see the difference. In here, we have two raw materials called ore1 and ore2. Each one has some amount of copper, zinc, and iron in them. We need to produce that amount and that amount and that amount of copper, iron, and zinc. The question would be then how to blend those two raw materials to receive the amounts of minerals that we need, okay? So that was the problem. The problem was cost minimization, because the cost per 100 pounds of ore1 and ore2 were provided, okay? And the amount of copper in the blend would be the amount per 100 pounds on ore1 of copper, and 40, that's for ore2. Together, it's how much you are going to get from the blend, and then for zinc, and then for iron. And it has to be at least as large as the required quantities. And in the optimal solution that we had last time, what we saw was that these two, so copper and iron were provided exactly as needed. You cannot go below. And zinc, to my best recollection, was the one that was more, because it was provided 650, well, you need 600, 650, so it gives you 50 pounds of surplus. And this was last time. Now here is another problem. It's number 15 in your book. So it's a blending problem. The differences are, first of all, we have here 3 ingredients. In this particular problem, probably we are talking crude oil. There are different ingredients because they come, say, from different wells, different locations. And one in Venezuela, and one in the Middle East, and one in Africa. So the crude oils don't have the same characteristics and qualities. This is why their unit costs, as you see here, are not the same. That's per barrel. Okay. Now, in addition, not only that we have 3 of them, where before we had 2, there is a maximum supply. That's what you have available of ingredient 1, ingredient 2. So there is a limit on how much you can purchase. Therefore, there is a limit how much you can blend. So this is one difference. The other one is about the products. You need to produce 2 types of fuel. One is characterized mainly by the different octane on them. So there is a requirement of at least 90 octane of the regular, at least 100 octane of the super fuel. And there is a different selling price for each one of them. And there is a maximum possible sales, because this is the maximum demand. So the company will not blend more than this and not provide to the market more than 350K of regular, not than 500K of super. Whereas before, it was the minimum demand required, then we didn't want to produce, in the previous problem, less than what the required is, because we didn't allow shortages. I would say that's because there was a contract to meet. So these are differences that lead to different formulation. The octane is the driving force here. It's what you need to meet. 90 octane means that on the average, a barrel of regular blend should have at least 90 octane in it, containment. So how do we approach this problem? We have a selling price, and you have a selling price and a unit cost. Naturally, we are going to maximize profit here. Now, the decision variables are blending variables. This is how much of ingredient 1 we are going to mix with ingredient 2 and ingredient 3 and produce fuel number 1, regular fuel. How much of the same ingredient number 1 and 2 and 3 we are going to mix in order to produce super fuel. Do you see that we have 6 variables here? It's the 2 by 3. This is a very small blending problem. It's larger than the first one, which was ridiculous. This one is coming closer to what you'll see in reality in terms of components in the problem, but still small. I've seen a problem, and it's not the largest that there is, 2 days ago, such a problem. It had 7 different ingredients because it's coming from variety of wells. Really, that's what it was. And the number of products were more than 10. A company in the petroleum industry who is buying these raw materials, mixing them and selling them, is producing dozens of products, dozens of them. So it's not only 2, like here, 2 types of oil, of gas. So that problem there had 70 variables. It was 10 by 7. Now it's becoming bigger. And they had a requirement not only on the octane, also you will not find it surprising on the amount of lead in the mix. Lead is an issue in gas. You see it in the gas stations. They indicate how much lead there is. So there were constraints not only on the octane, but only on the amount of lead. And different products have different amount of lead. So you have to watch it when you blend, you are not going over what is allowed. And if you think that lead and octane are the only characteristics, no, there are more. I just don't want to extend on that too much here. In this problem, we are trying to maximize profit. So the profit for an ingredient 1 that is mixed with others to be sold as a regular fuel, the profit per barrel will be $18.50 selling price minus $16.50 purchasing cost for ingredient 1. 20 minus 16.5 is the profit on a barrel of super gas that was created by ingredient 1. So when you add all of them, you get the total profit. So again, this is the profit that you gain from selling a barrel of regular gas from the ingredient 1 portion of it. You have another profit from if you mix it from ingredient 2 and 3. That's the total profit. So with these variables, here are the constraints. You have 2 groups of constraints that you'll find it very natural to understand. And then I want to talk about the third one. The supply constraints have to do with how much of the ingredients is available. So whatever you blend, you cannot use more than 110,000 barrels of ingredient 1. You use it for regular gas and super gas, so that sum has to be less than or equal to 110K. This is true for ingredient 2 and ingredient 3. So these are the supplies. These constraints were not in existence at all in the previous question because supply was unlimited. So you didn't have any constraint. Now the demand constraint, whatever you mix, do not mix more than 350K barrels of regular because that's the maximum demand. And so is for the 500K for the super. So you see ingredient 1 mixed to create regular plus ingredient 2 plus ingredient 3. This is what you mix in order to get regular gas. Should not be more than 350K. So these constraints, I think, are very intuitive. Now comes something to understand about the octane. You have to meet an amount of octane in a blend. This, because they are mixed of different ingredients in different quantities, the 90 that you see for regular is the average per barrel of the mix. So how do you calculate the average octane? I'll give you an example, then you'll understand. I take 1 barrel of ingredient 1, I take 1 barrel of ingredient 2 and mix them. I now have 2 barrels. What is the octane of this mix? 100 times 1, 87 times 1 divided by 2. 1/2 and 1/2 is the relative weight of each one of these 2 ingredients in a mix of 2 barrels. Okay. Now, if I take 2 barrels of ingredient 1, 2 barrels, and mix it with 1 barrel of ingredient 2, here. So I'm going to get 100 times 2 plus 87 times 1, the total octane, divided now by 3. I think my gardener is making a lot of noise here. Okay, that's what it is. Okay, I'm sorry. And now, if you are looking at the overall blend, so you take 100 times ingredient 1, 87, and 110 of ingredient 3, and then you divide it by the total quantity, and you multiply by the variable that goes to the regular gas, then you have to have this greater than 90, the same for the super, greater than 100. Okay. There is no problem in writing these constraints. The problem is understanding how to solve it because these 2 constraints are non-linear. When you have a constraint is a ratio, and the ratio includes variables in the numerator and variables in the denominator, you have a nonlinear function. You can enter it in solver like the other constraints and go to solver and go to simplex and try to solve it. No solution obtained. Solver will stop you and will tell you that either the conditions for linearity are violated, or it might tell you some weird things that you try to divide by 0 and I can't do it. Or it might tell you there is no feasible solution to the problem. Some statement on the screen will tell you that you cannot solve it with the constraints as is. This is where I'm going to excel now and show to you what we do in order for solver to be able to solve it. What you see here, this is, by the way, the problem itself on the left here from our book. And so I put it here so if you want to read and understand the model better, it will be more convenient. And now let me delete the solution because we will get it anyway in a minute. Let me go over the model. Then I'll go down to the 2 constraints that I copied from the PowerPoint. See? So, and we'll talk about them and how we overcome the non-linearity. First, you see here 6 variables. Here, I left room for those values of these variables. Here is the profit per variable. So 2, for example, is this 18.5 minus 16.5 that probably you remember. These are the supply constraints because it's about the availability of each ingredient. As you see, the quantities on the right-hand side are what is available. I wrote less than or equal to as I should. And the sum product here is calculating exactly how much of each ingredient you are using. That's why you put 1 and 1 here for ingredient 1, ingredient 2, ingredient 3. Each one of these ones belong to the variables in question. Ingredient 1, you put 1 and 1 here under ingredient 1 and ingredient 1. You put 1 and 1 here under ingredient 2 and 2, and so on. So you should be, this should be familiar to you because we did it before twice, and I put ones and zeros whenever it was needed. That's what I did here, only that I didn't enter zeros. So this sum product, for example, what it calculates, the total amount of ingredient 1 used. How? 1 times the quantity plus 1 times the quantity plus 0 times plus 0 times. So you see only these two quantities are added, and this together here should not exceed 110,000 barrels. That's ingredient 1. And the same here and the same here. Okay. And the sum product, to remind you, you see you write sum product, and then you take the first vector here, comma, the second vector here, close parenthesis here. You put the $sign on the first vector by pressing F4 after you enter it. And now we have this sum product ready. I separated it here so that you see group by group, just for us to talk about it. As a matter of convenience, you may write them under one another and then copy and by dragging all the sum product. Well, I can do it now. Take a look. You see what I don't like? You see what it does? It put a 0 here instead of the word used. And I put the word used because I want it here, because it's meaningful. Okay, so you can do it, drag everything down, and then enter titles here if you want to. I like it because it makes the model more clear, even for me. And it's especially important when you have a very large model. So after the sum product were entered, everything is ready, but here are the octane and for regular and super fuel, and I have to explain what happened here. So I'm referring now to the regular ratio here, and I notice that the numerator as is a linear function. You see, you don't see any variable with a square or square root here. So is the denominator. So if I could separate between them somehow without affecting the fact that the ratio has to be greater than 90, then I could get maybe a linear constraint. Here's exactly where I'm heading. I take this denominator from here and move it to here. What did I do here? 90 times this sum. Now you have a linear constraint because both functions on the left and on the right are all linear, and this is legitimate, and Solver will understand it when you enter it. That's all. That's the trick. The same way you will do to the next one. So when you see the two constraints here, here, this is exactly what I did. First of all, on the left-hand side for this first constraint, 100 87, 110 is 100, and then 87 and 110 under each variable appropriately. And then you write sum product and it calculates the sum. Here, you calculate sum product and it calculates the sum because you have the coefficients. And on the right-hand side, see what I did? 90 times a cell called V14. Where is V14? This is the one. Because I have to take 90 and multiply it by the sum of the regular blend. Well, this one is calculated here. This is the regular blend. So I just take advantage of this sum already present in the model, and I multiply 90 by this sum. Then I do the same for this one. For, I don't know why, for this one. So, see, now it's V15. This is it. And now the model is ready and it's linear, and we can go to solver and solve it. So we go to data here and go to solver. The model is already in, so let me just make sure that you see that it's already in. V6 here is our, V6 is our objective. The variables are all the 6 here. The constraints, so the first group of constraints, here it's written the last one, it's V9 to V11. V9 down to V11 is less than X9 to X11, and you can see it here. Same way I enter the rest of the constraints. The only thing I want to mention to you that I took advantage of the way the constraints are written. Do you see a group of constraints, all of them less than or equal to? So I can enter all the sum products in one hit. You just, on the left, when you see the window, and on the left, you enter the left-hand side sum products. Well, you can select all of them together. All of them together. And you have all of them written as V9 to V11, and you don't have to do it one at a time. And on the right-hand side, you'll select the X9 to X11 in one selection, and you enter 3 constraints. And then 2 more, and then 2 more. They are all the same sign. When you do all this and you solve the problem, here is the optimal solution. This is telling you what is the optimal blend that maximizes profit. So ingredient 1, 110,000 barrels of ingredient 1 are used to produce regular gas. Of course, you need to mix it because you need more than 110 barrels. So you mix it with ingredient 2, and you don't mix it with ingredient 3. And for the super gas, you don't take ingredient 1 at all, but then you take 2 and you take 3. And these are the quantities. And you see, if you have a small problem, well, maybe an expert could find it himself. When you have a large number of ingredients, the quantities, you can't really know it. You have to find some mathematical method that will give it to you. And these models are very popular for one simple reason. Not only the complexity that makes it possible to manage it, it's the cost or the profits. We are talking here many, many hundreds of millions of dollars. And these models make it possible for you to save money or to increase your profit. Very popular models. Okay, so now what is left here is just to go to, for a few minutes, short visit of the sensitivity analysis. I'll come back to this problem. So it's just a brief discussion of sensitivity. I want you to see what's provided there, only partial analysis, not more. And we'll go back to this next week, same problem. And because you need to know it before the test, I want you to be able to handle sensitivity analysis. So I'm going now to run sensitivity analysis on this model, you see? And so I solve it first, and then sensitivity analysis is requested. And I get a report here on the left. And this is the report. Okay. Okay, so I don't want to discuss those values here on the allowable increase and decrease. They're kind of weird. This is 0 and this is infinity and 0 and 0. So weird things are happening here. To some of them, I'll refer to in our next meeting. I do want to talk about this allowable increase and decrease because they are more intuitive. It is talking about the right-hand side of the constraints. Remember, the sensitivity report on the lower part of it is talking about the range of feasibility that allows the right-hand side of each constraint to move right and left without changing the shadow price. So just to reiterate the shadow price and what does it mean is the following. For example, I'll take one that has a shadow price that is not 0. This is the constraint on the demand for superfuel. The demand is for 500,000 barrels, maximum demand. What the solution is calling for is meeting this demand. You see, this is exactly how many barrels of superfuel you're going to blend. So what would have happened if this would require 1 barrel more? Then you will produce 1 barrel more and you will make $1.50 of this additional barrel. And how do you know that you can use the 150? Because the allowable increase is way more than 1 barrel. So 150 applies all the way up to an increased demand of 307.69 barrels more, 30,769 barrels more on the demand side, and you will still make $1.50 on each additional barrel of demand. And you know what it means? It means that you are going to sell. You are going to meet this demand. Because if you don't, you will not make $1.50 on this additional unit. But if this is true, then this solution is going to change. Because now you have to meet 1 barrel more that you didn't have to meet before. So the solution is going to change. So what is the new production plan if you have larger demand? Sensitivity analysis doesn't tell you that. If you really insist on what is the new optimal blend once the demand to super is increasing, you have to resolve the model. What you do not have to do, when do you not have to solve the model again, is if all what you want to know, what will be the new profit? The new profit per barrel will be $1.50 added to the profit. So 1,000 barrels more will add 1.5 times $1,000 to the profit. The arrangement here will be different because you'll have to meet a new demand that you didn't have to meet before. The totality of this change in terms of profit will be $1.50 per barrel times 1,000 barrels. So that's the shadow price, and there are other shadow prices that can be interpreted this way. There is one shadow price that is 0 here, and more than one, and this tells you that, okay, the amount of octane, of regular octane, ended up being more than 90. If you want to see, I'll show it to you that it's true. Okay, so look at this constraint. You see, this is the octane of regular gas. 200, okay, so the left-hand side, if you compare it to the right-hand side, then this one is larger. If they were equal to one another, then you meet exactly 90 octane in your mix. But this one is larger than this one. This means that your mixture has more than 90 octane in a blend. This one, for example, has more than 100 octane. Well, that's for the super, again, because it's larger. So once it's larger, if you increase the octane required here by 1, then this one is so much higher than this one that nothing will happen. You are already more than 91 octane. We can check. We can put here 91 instead of 90 in the calculation here, and to see if it is meeting this value. If it's still not meeting this value, it doesn't matter if you require 91 octane, because you already are providing more. The shadow price will be 0 because the profit will not change. You don't have to change anything in your production plan. That remains feasible. So therefore, when I go back to the sensitivity, there is a wide range of values here of increasing the requirement on the octane side without any change in the profit, so the shadow price is indeed 0. So more on this in our other problems that we'll do next week, you'll see. Our transportation problem will be very interesting to see, and we'll have similar situations. So that's what I wanted to talk about in terms of sensitivity. I'll stop the sharing at this point because I want now to close this, start the conversion to a file, and send to you the Excel. Any questions? Okay.